thank you very much, Giovanni, for giving me this opportunity to present this work and for organizing such a very nice and lively conferences. So indeed, maybe I can use round questions to introduce the presentation. Here we will probably look more at what we can do from having from light to spin conversion. And in fact, indeed, I'd like to show you a system where we are able to switch the magnetization of a ferromagnet with a single femtosecond laser pulse. So we just shine, as you can see on the drawing, and that's basically the conclusion of my talk. We come with a laser pulse, which is about 30 femtosecond. We come on a magnetic layer, gadolinium cobalt, which is going to be demagnetized. We are going to be able to create a current pulse, which is extremely short and polarized. And this current pulse will switch the magnetization of a cobalt platinum layer. So we'll have the switching with a single femtosecond laser pulse. So indeed, what we're trying to do here is to go toward ultra-fast spintronic. And as it has been shown, when you combine magnetism and electronic, you deal with spintronic. Here we introduce another degree of freedom, which is the ultra-fast optic. And by sharing those three different fields, we hope to open this ultra-fast spintronic field. So what do we have to do? So first, we have to generate ultra-short current pulse. And we have to make sure that those current pulse, we can polarize them and we can inject them into a spintronic structure. And then once we have done that, we have to be able to observe the interaction between the current or the spin current with the magnetization and see if we have observed switching. So in terms of fundamental interest, I think it's very interesting because this is really highly so the dynamic here is extremely interesting because we are at very short timescales. And at those very short timescales, we can describe our materials with three different bands: the electron bands, the spin bands, and the lattice. And we can even attribute a temperature to those bands. And of course, the electrons are going to be heated up much faster than the spin and then the lattice. So basically, the fundamental questions here that we want to work on is how do we transfer energy from one band to another? How do we transfer angular momentum? How can we transfer charge and spin currents? And once we have understood how we can do that, then it's going to be much easier to deal with this ultra-fast spintronic field. If we look at it, the starting point is really the observation of ultra-fast demagnetization observed in 1996 by the group in Strasbourg with Eric Beaurepaire and Jean-Yves Bigot. And what they observed, and many of you have probably seen already this curve, where we observe the magnetization of the nickel basically as a function of time, and we can observe an ultra-fast demagnetization. So an ultra-fast heating of the nickel spins leading to this demagnetization. How they were able to do this measurement is basically a pump probe experiment, and we'll deal with pump probe experiment in the future. So let me just very quickly explain it. You have first a pump with a certain wavelength. Here it's 800 nanometer. And so this pump is the one that is demagnetizing the nickel. And then you have a second pulse, which is the probe. And this is basically in order to observe this demagnetization as a function of time. And just by changing the delay between the pump and the probe, you can create this curve. So this was the first observation of this ultra-fast magnetism. It is interesting, and it's again to show that combining this ultra-fast magnetism with spintronic, we can, because we will be out of equilibrium, we can hope to be energy efficient. Basically, you just have to heat up the electrons, and you don't have to heat up the whole system to see many of the effects. And we can be extremely fast because we are dealing with extremely fast stimulus. One thing that I'd like to advertise, but I will not be talking about, it's a work done in the group. Jan Gorchon was leading this subject together with Koshalia, his PhD student. And what they were able to create is a very short electron pulse of about 3 picoseconds. And using SOT, spin orbit torque, they could switch this single cobalt layer with this one of this single electron pulse. So if you want more information, you may look at this publication. What I would like to talk about today is really dealing with ultra short current pulse that are generating by the femtosecond laser. So first we will see how we can generate this ultra short current pulse. Then we will see that we can use this ultra short current pulse in order to create ultra fast demagnetization. We will use also the same current pulse to observe the switching of this very special material, which is called gadolinium iron cobalt, a ferromagnetic material. And then finally, I'll demonstrate that with this current pulse, that is then a spin current pulse, we can switch the magnetization with a single pulse of this cobalt platinum layer. And we have new results showing that this magnetization switching can be even very fast. So let's first here prove that we can generate a very short current pulse, and that this very short current pulse can induce a demagnetization, ultra-fast demagnetization, comparable to the one that has been observed by Eric Berger and colleagues. So our setup, our system is this one. We will have a pump, we will pump from one side. The pump is going to reach first a platinum layer. Then there'll be a copper layer, which going to be tuned. We will change the thickness of this copper layer. And then we will have a cobalt platinum, our magnetic materials. And this is the cobalt platinum that is going to be demagnetized. And to observe this demagnetization, we will have the probe on the other side. What is clear is that if you change the copper thickness, that's what we're going to do. If you have a copper thickness that is more than 50 nanometer, maybe 80 nanometer, there's no way that this light can interact with the cobalt platinum. It has to be something else, and will show that this must be hot electrons traveling into the copper. Indeed, what you see here is exactly the curve of fast demagnetization that I've shown you for nickel, but this is for the cobalt platinum. And you can see those different curves are the ones obtained with different copper thickness. So the reference layer is there's no copper, so you directly you directly have the light interacting with the cobalt platinum. But then for the other thicknesses, 80 nanometer to 300 nanometer, there is no way that the light can interact directly with the cobalt platinum, but still you observe this ultra-fast demagnetization. And so looking at the differences that you can see is that first there is a delay. So the demagnetization doesn't start at zero, you have to wait a little bit. And secondly, you have a broadening of those curves. So we look at the delay and the broadening of the curve in order to give a number of the speed of those hot electrons traveling into the copper. Oops. Okay, so yeah, so here we can have with delta T0 an idea of the delay and delta tau the broadening of the curve. And you see that those two numbers are almost linear with the copper thickness. So basically we can say that those electrons travel almost ballistically into the copper. And if you look at the velocity that is obtained are very similar to the Fermi velocity. So it can only be electrons traveling that fast. Secondly, we looked at what is efficient in order to create those electron pulses. So we put it first platinum. And indeed, if we put platinum or even cobalt platinum, this is quite efficient to observe the demagnetization. If there is no platinum or MgO, then it's less efficient because this is only the light that can interact with the copper that will generate those electrons. Secondly, if we focus just on platinum, there is an optimized thickness, which is here shown as being 7 nanometer of platinum, in order to create enough electrons that are going to be traveling into the copper. And from our results, it sounds clear that from until 200 nanometer, this is quite ballistic. We need almost the same laser power to demagnetize the cobalt platinum, whether we have 100 nanometer of copper or 200 nanometer of copper. So what we've demonstrated here is that we can generate from a light pulse, short light pulse, 50 femtosecond, we can generate an electron pulse about 50 femtosecond as well, and that this electron pulse can demagnetize ferromagnetic materials as it was possible to do it with light. Now, we will now concentrate on, can we use also those hot electron pulse in order to switch a gadolinium iron cobalt or a gadolinium cobalt layer. Those gadolinium iron or gadolinium cobalt layer are interesting materials. They are ferromagnetic. So you see that there are two sublattice, the rare earth and the transition metal sublattice. And if you adjust the composition to a certain point, then you can have compensation, meaning that the magnetization of one sublattice is equal to the magnetization of the other sublattice. So the net magnetization is close to 0. And so we have grown many different layers around this compensation. So you can see the different concentration here. What we see is that when we change the concentration, you see that the hysteresis loops symmetry changes. And that's a proof that we went from one part of the on one side of the compensation to the other side. So on one side, you are gadolinium rich. On the other side, you are transition metal rich. And you can pick up this compensation point because the magnetization here, the point in blue, goes to 0, but also the coercivity diverges at this point. And if you take those materials and you send just one light pulse, a 50 femtosecond light pulse, you can reverse the magnetization. If you send a second pulse, you'll reverse it back. And it does not depend on the orientation of the magnetization. So here, I forgot to tell you, but the magnetization is out of plane, and you can go from up to down just by sending one single femtosecond laser pulse. We were recently able to create a state diagram. So basically, we wanted to determine for which pulse duration and which fluence. So the fluence here is basically the integrated energy. So if you have a given fluence, then you have a given integrated energy. So we plotted here the pulse duration as a function of the fluence, and we checked if the magnetization was switching or not. So of course, if the fluence is too low, especially if the pulse duration is high, then there is no switching, nothing happened. And if your fluence is too high, then you're going to be demagnetizing because you raise the temperature too much. But there is a cone here where we can observe the switching. This depends on the pulse duration, as you can see. So we took those materials, gadolinium iron cobalt, and we put it into this kind of structure. Again, same thing, platinum, here 5 nanometer, some copper, and then gadolinium cobalt. And we made sure again that this pump could not reach the gadolinium cobalt, so that it had to be mediated by electrons. So we took pictures for different concentration that you see here, and then concentration are above and below the compensation. And on the first row here, you have the result obtained with light only. So we just shine light. And you see that with one pulse, you switch. Second pulse, you switch it back. Third pulse, you switch again. Fourth pulse, switch it back. And those different points here corresponds to different laser fluence. if you increase the laser fluence, then you increase the diameter of your laser. If you don't do it with light, but with electron, because of this device, you have exactly the same phenomenon. So this single pulse switching can be obtained with light, but also with electrons. What's also interesting is that we looked at the dynamic of this reversal. And so you see, this is the Kerr signal, so that's basically the magnetization as a function of time. And this is obtained for direct laser illumination and the use of hot electrons. And you see that the dynamic of the reversal is very similar. First, a fast demagnetization. Here we are on a logarithmic scale, and then slowly it reverses. Slowly, well, it takes between 10 and 100 picoseconds. And so what we've demonstrated here is that with the light pulse and the electron pulse, we could switch it, and we would switch it the same way as fast for laser and for hot electron pulses. Now, let's talk a little bit about this gadolinium iron cobalt, because we will use it. The reason why it switches is certainly related to the fact that the relaxation time for the transition metal, here the iron, or the rare earth, here the gadolinium, is different. And because you have a different relaxation time, you can come to a point where you have a transient ferromagnetic state and then a switching. What's also interesting is that if you eliminate this kind of materials, so if you demagnetize, when you are demagnetizing such material, or if you demagnetize any magnetic materials, you have a DMDT, you demagnetize, you change the magnetization. If you think about angular momentum conservation, this means that you will have current pulses in order to have angular momentum conservation. But here, because of the two relaxation, you will have a first pulse that is mainly due to the relaxation of the transition metal, here in blue, and in red, mainly due to the relaxation of the gadolinium. So we believe that if we shine light on this kind of materials, we will have kind of two current pulses of different polarization. And that's what we use in this system. So gadolinium iron cobalt, copper, cobalt platinum, in order to switch the cobalt platinum with a single laser pulse. So we have grown those three layers, gadolinium iron cobalt, copper, cobalt platinum. You can see the hysteresis loops showing 4 different states, because you have 2 parallel states here and here where the magnetization are parallel, 2 anti-parallel states when the magnetization are anti-parallel. We made minor loops in order to make sure that there was no exchange coupling between the 2 layers. Because what had already been observed is that you can switch gadolinium cobalt, as we have done before, and because of exchange coupling, we can reverse the cobalt platinum. So what we think is happening is this: we come with a laser pulse, we demagnetize the gadolinium iron cobalt, it leads to 2 electron, 2 spin current pulse, and the one that is going to switch the cobalt platinum is the one that was created by the demagnetization of the gadolinium. And indeed, if we have those different colors, so here you see, to understand this graph, we came with a laser pulse of different fluence. So low fluence on top, high fluence on the bottom. If we go from red to blue, this means that we're going from a parallel state up to a parallel state down, P minus, meaning that we have reversed the cobalt platinum. If the fluence is not high enough, then you can see that we are only reversing the gadolinium iron cobalt in that case. And each time you send a pulse, each time you can reverse both three. And what is interesting is that if you have a high fluence, that means that the energy in the center is high because it has a Gaussian shape. When you move away from the center, you will have a lower fluence. So the reversal on the outer part of this spot is exactly what you observe for low fluencies. Okay. Yeah, so what I'm trying to say here is that if you look at the diameter, if you move away from the center of your pulse, so if you increase the diameter, you can see a different pulse energy. And that's what we could come up with. So basically, we can come back to this state diagram where we see that for low fluence, there is no switching. For intermediate fluence, there's the switching of the gadolinium cobalt only. And we have the switching of both layers with a single pulse if we have a fluence that are high enough. In order to make sure that the reversal is due to the spin polarized by the gadolinium, we could change the concentration. So we've changed the concentration of the gadolinium from iron cobalt rich to gadolinium rich. And each time we observed that what mattered is not the direction of the magnetization, but indeed the direction of the gadolinium compared to the direction of the cobalt platinum that's going to be reversing. Also, can we block the spin current? And we thought, well, let's put an MGO layer here. We will be able to send the laser pulse, but the current is not going to flow into toward the cobalt platinum. And yes, by putting this MGO insulator, then we can no longer observe the reversal of the cobalt platinum. Now we put it also some platinum layer into the copper in order to depolarize the spin current. And we did that for different thickness of platinum from 0 to 4 nanometer. And we can already see that we have a full reversal when there's no platinum. But as you put platinum, you certainly depolarize the current coming from the demagnetization of the gadolinium. And so because this current is no longer polarized, it can no longer switch the cobalt platinum. And you see a switching of the cobalt platinum that gets lower and lower. So, and another point when we did this experiment is that, as I explained, the gadolinium cobalt was also switching. But do we really need the switching of the gadolinium cobalt in order to observe the switching of the cobalt platinum? And the answer is no. You just need to demagnetize it. So by changing the gadolinium iron cobalt concentration, we were able to create a material such that the light comes on the gadolinium iron cobalt, it demagnetizes it, it's not switching it, so that means that it will come back to its initial state afterwards, but it does switch the cobalt platinum. And so what really matters is the derivative dMdt, and having a gadolinium iron cobalt demagnetization is sufficient to observe the switching of the cobalt platinum. All right, and then oops. What we also played with is we played with the Curie temperature of the ferromagnet. Remember, we started by cobalt platinum, and then we did cobalt nickel multilayers. And what's interesting about this cobalt nickel multilayers, just by changing the thicknesses of the cobalt and the nickel, you can tune the Curie temperature of the materials. So when you tune the Curie temperature of the materials, you also change the exchange coupling inside these materials. So what we observed, not super clear on this graph, but the fluence that you need to observe the switching depends on the Curie temperature of your ferromagnet. If your ferromagnet has a low Curie temperature, then you don't need much energy in order to demagnetize it enough such that the cobalt nickel is demagnetized enough to be reversed by the spin current coming from the gadolinium. If you increase the Curie temperature, you need to have more fluence in order to bring the cobalt nickel close to the ordinary temperature. So just to conclude on the mechanism here, what we understand from all those measurements is that first we observe that with a single laser pulse, we can switch the cobalt nickel, that this is certainly mediated by a hot spin current, that this spin current is due to the demagnetization of the gadolinium. And you create this spin current that will interact with the cobalt nickel, which already is quite demagnetized. So the cobalt nickel is demagnetizing because of the flow of electrons or even the light. And then when it's demagnetized enough, you have the spin currents that allows to switch. And so in conclusion, we can say that what we've done is that we were able to show that we could generate ultra short current pulse. So we have some kind of ultra fast spin pumping. We can manipulate this ultra short spin current. We can inject, and it can be polarized. And then we can transfer angular momentum even enough to a ferromagnetic layer to switch it. And the last result that we are observing right now is that we can say that we can have an ultra fast switching of the ferromagnet. And I will really finish with this slide and thanking all the people I had the chance to work with on this project. And thank you very much for your attention.